Recording. Oh, thank you, Rishi. Ahead of me. All right. Hey, great to see all of you folks. I'm really, really happy to be back with you. Really happy to be back with graphics in our course. And as I wrote on Piazza, I am sad that I missed out on the chance to teach you about all the great topics that have been covered in my absence. I'm really happy that Professors Kanazawa, O'Brien, and then Matt Tansik were able to cover most of the lectures live for you folks. And a lot of great topics were covered that I've said I wasn't able to teach you myself, but I'm glad that they got covered so the course can keep going. Today, we're going to talk about Monte Carlo integration, which is a really big hammer, right, in computing, a really, really powerful general computing tool that I hope that in learning it today, if you haven't seen it before already, or if you have, deepening your sort of exposure to all the things you can use it for, that you'll just find this is so useful in your career in many, many different technical tasks that you'll go into, many different areas of engineering and science. And we're going to cover it today in a general sense. And then tomorrow, we're going to talk about applying it specifically to the global illumination problem, which is synthesizing images that look very realistic from a lighting and materials perspective, which is going to turn out to be solving these really high dimensional integrals, okay, numerically. All right, so with that sort of preamble, Monte Carlo integration today, global illumination on Tuesday. Let's get going. So what are we talking about here? We're talking about numerical integration. Okay, as a reminder, typical way we do numerical integration is something that, the jargon is quadrature, right? Quadrature. So let's say that we have a definite integral here that we want to evaluate, some integral of f of x between a and b, x equals a and x equals b. Okay, so in quadrature, we would take a set of subdivisions of this interval in x from a to b, as shown here, and then we would evaluate the function at each of these endpoints here of these subintervals, and then we would estimate the area under the curve, right? Remember, this is like calculus 101 by some kind of procedure. It could have rectangle rule. Here I drew the trapezoid rule. You might remember Simpson's rule, that kind of stuff. Okay, so this is quadrature-based numerical integration. That's not what we're going to talk about today. Okay, we're going to do it in a randomized sampling manner. That's what Monte Carlo integration is trying to solve the same numerical estimation problem, but with randomized sampling. And as motivation for why we're going to do it that way, let me describe some of the integrals that we're going to be dealing with. I'll use examples from graphics, but of course, integration is like just everywhere, right? Across engineering, across science, across data science, across any sort of technical discipline that you can imagine. Let's see a few examples. 2D integrals. So recall when we did anti-aliasing of rasterization of triangles into the frame buffer, one of the ways we did anti-aliasing was to recognize that you could try to take those triangles and calculate the area coverage. So how much of a particular pixel's square area was covered inside the triangle that we were rasterizing. Okay, and then we'd draw the pixel value as that fractional value of red or teal as shown here. And we estimated that by supersampling, if you recall, and you all did in the assignment, right, by n supersamples inside the area of the pixel. If you think about it a little bit, that is quadrature-based numerical integration of the fraction of that pixel area covered by the triangle, okay? Point sampling versus area sampling. But there's a 2D integral there that we're calculating. Another example that you touched on yesterday, or on Tuesday rather, with Professor O'Brien has to do with calculating quantities in lighting measurement. You covered this concept of irradiance, okay? And if you want to estimate or compute the irradiance from the environment at a point on a surface, then there was this expression, the irradiance E at a point P on a surface, was given by this integral. It was the integral over the hemisphere, right? The dome that sits over that point on the surface. integrated over d omega, omega being the directions in all the different directions in angle contained within that hemisphere. And it was integrating L, which was the L sub I, which is the incoming radiance from that angle towards that point P. Okay, P and then omega giving the position on the surface and then the direction. And there was a weighting term cosine theta due to Lambert's law. Okay, so this is the integral that one would cover, that one would want to compute in order to estimate the irradiance on the surface. So that's another example of a 2D integral, but this time in something akin to spherical coordinates. Let me give you an example of a 3D integral. Okay, if you try to incorporate the visual effect of motion blur, as you see in this, it's not a photograph, this is actually a very famous computer rendering that was one of the entry points into using Monte Carlo integration for computer graphics. You can see here what, there's a cue ball, right? The ball at the bottom that struck the 9 ball, which is blurred out. And the 9 ball has then struck the 8 ball, which is now ricocheting. And the 8 ball has just started to strike the 4 ball, which is starting to move. Okay, but for most of the duration of this virtual photograph, of the shutter duration of this virtual photograph, the 4 has been stable. That's why it's mostly looks like a 4. But if you look closely, you can start to see its motion. And the only ball here that's really crystal sharp is the 1 ball, because it hasn't moved at all, okay, during this time interval. So if you think about the value of every pixel inside this virtual photograph, there's the 2D integration over the area of the photograph, similar to rasterization. But there's also the integral over the time domain, right, of the motion in this scene. So the 3D integral here would be over xy of the pixel and then t. Here's an example of a 5-dimensional integral, okay? Same as before, the 3 dimensions of x, y, and t. But then if you look at this photograph, you'll notice that there's lens effects. In particular, it's focused on this hummingbird here, but the background is blurry. This is what it looks like to us in the real world. Like if you look at your fingers close to your face and you sort of pay attention to further objects, you'll notice that they're out of focus because of the lens effects of the optics in our eyes. Same effect as in our cameras. It turns out that the integral here is not only over the XY extent of the pixel and time duration, but also over the area of the aperture, the opening in the lens, either in our eye, in the pupil, or in this case of a photograph, in the opening in the lens aperture of the lens that you're using on the camera to take this picture. Okay, and so you have to integrate over that area as well. In fact, I'm not going to belabor this at this point, but you can actually write this down to show that this really is an integral. You can write it down specifically in terms of L, again, the radiance that's coming in the scene. This is a schematic for inside the camera body. This is the lens aperture. That's a position P prime over this lens aperture. That's the opening in the lens. Here's the sensor plane where you might put your CMOS sensor inside the camera. There's a position P here. So this is L, the radiance that's traveling from P prime to P here at a particular point in time. It turns out if you run the radiometric calculation, there is cosine to the 4th of theta, theta being this angle here, and it's integrated dp, dp prime, dt, okay? And there's a 1 over d squared here if you run the radiometry. I'm not going to derive that here, but this is actually the integral that one will calculate in order to estimate the irradiance on the sensor plane inside a real camera for an image that corresponds to something like this, okay? L is the radiance, okay? And you remember from the radiometric descriptions last time in lecture, which I encourage you to take a bit of time to familiarize yourself with. It's sort of like SI units and then derived quantities of SI units or something that, it's sort of like physics. The first time you see it, what is this? Like, what's energy? What's power? All those kind of things. It's a very similar sort of familiarization with the various derived quantities related to measuring light. So in this case, the L here is radiance, and the Q in this is going to be actually the exposure, the total energy deposited at the pixel area over the duration T0 to T1 of the shutter being opened and exposed to light in the world. But the details of that, the integral, again, is not critical. I don't want to spend too much more time sort of belaboring the point, but the key point I want to say is that there is an integral there. You can write it down, and you can aim in what we're going to be doing in physically based rendering is to derive those integrals from first principles radiometrically, and then we're going to aim to calculate those integrals numerically as accurately as we can. Okay, so that's a sort of bit of motivation in graphics for where integration and complex integration of this kind, complex in a complicated or a sophisticated sense is going to arise. As soon as you start to think about high dimensional integrals, this thing called the cursive dimensionality comes to play right away. So in high dimensional integration, the problem is that the higher the dimension, the more samples you need to take in a geometric sense with respect to the dimension. In particular, let's say you have a d-dimensional integral. I showed you 2D examples, 3D examples, 5D examples. There's going to be a lot more higher dimensional examples too. But let's say it was 5D, for example. Okay, d equals 5. The cursive dimensionality is that the total number of samples you need to take in order to sample that 5-dimensional domain of integration, right? It's a 5D integral, is going to be, say, n samples in each dimension, but you have to multiply them all, right? Because each dimension is independent, is orthogonal. So you have to do little n times little n times little n 5 times, so it'd be n to the 5th power for a 5-dimensional integral. This goes up really quickly with the dimension, as you can see. And part of the problem is that the numerical integration error, it's going to fall with proportional to 1, it turns out, proportional to 1 over little n, the number of subdivisions in each of the dimensions of integration. So if you draw, for argument's sake, 10 samples, little n being 10, so 10 to the 5 total samples for a 5-dimensional integral, then, the error is falling as 1 over 10, but you've drawn 10 to the 5, you've drawn 10,000 samples. Wait, 10 to the 5, no, take it back, 100,000 samples, okay? So the error falls pretty slowly with respect, in comparison to the total number of samples that you're taking. And each sample is expensive because you got to draw it, you got to evaluate the underlying function in order to contribute to your estimate of the integral. Now let's contrast that with a random sampling error, okay? And we're going to do random sampling estimation of this Monte Carlo, of these definite integrals. Random sampling error falls in a very different manner. You can think of the error in random sampling as falling as the standard deviation, okay, of that estimate, of that random estimator. So it falls as the square root of the variance. For many random sampling schemes, the variance is proportional to n. Okay, so it turns out that the error is going to be proportional to 1 over square root of n, or capital N here. Capital N, again, is the total number of samples that we draw of evaluating function f in order to estimate the integral that we care about. Now, this is a lot better, right? N to the half is a lot better than n to the 1 over d if d gets really high, if the dimension of the integration domain gets really high. Okay, so that's the key here. For high dimensional integration, random sampling starts to win. All right, that's what the sentence basically says. And this is compared to what? Compared to quadrature-based numerical integration, which you can think of as uniform, regular sampling of, exhaustive sampling of the grid-based sampling of the integration domain. And I showed you 2D, 3D, 5D examples, but it turns out next lecture, we're going to look at global illumination in all its full complexity and glory and find that global illumination actually entails infinite dimensional integrals. Okay, we're going to derive that together and see why it emerges that way. Question, what is the lowercase n here? Someone asks. Good question. So the lowercase n here is the number of samples in each dimension. Okay, let me go to a 2D example. Okay, so if you got a 2D domain and little n is 10, then you have 10 samples in x dimension, 10 samples in y dimension, which is 10 by 10 samples because you have a 2D grid. Okay, so capital N in that case would be 100 and little n would be 10. Let me show you an example of this. It's a little bit of a simplistic example, but I think it will convey the point in a certain way. Let's look at discrete or quadrature-based estimation of an integral versus Monte Carlo for the case of shadow calculation. Okay, shadow calculation. Now, this is a test scene here. It's got a light source just floating in the middle of space. There's an object here, a polygon, just a little square here, floating in space. That's a blocker. And there's a ground plane. And what's happening is that the light source at the top is casting light onto the ground plane, and the shadow is being cast by this floating blocker. If we do quadrature-based integration in this case, then what happens is that in calculating the light intensity of every point on the ground plane, every pixel that's on the ground plane, we will cast a ray from that towards the light source in quadrature, you've got to pick one sample location. So if we have only one sample, then a structured way to do it would be, like, say, to cast it to the center of the sample, center of the light source, and you see whether or not it's blocked by the this blocker over here. If it's blocked, then no light's transferred, you get a shadow, okay? If it is not blocked, like you actually hit the light source, then the light's transferred and you get an illumination, okay? So you can see you get like a square shadow over here. But this is not actually the correct answer. This is over here, a different picture, has a error too, but a different kind of error. It's a noisy error. What's happening here is a Monte Carlo estimation of this lighting integral. And instead of casting a ray from the ground plane to the, say, the same location, okay, inside, say, the center of this light source, we're casting it over a random position on this light source, okay? And what you see, that's the only thing that's happening is different between these two. And what you get is instead kind of a soft looking shadow here. You can kind of see it's kind of fuzzy. It's very dark right underneath the blocker. And that's right, this blocker here. That's because no matter which direction you try to cast a ray towards the light, it's always blocked. The blocker is big enough that it blocks every position of the light source. If you're outside the, we'll call this a penumbra, is the soft part of this soft shadow here. If you're outside the penumbra of that shadow, no matter what position on that light source you try to cast a ray to, it's always going to get there. The blocker doesn't block it at all, so it's fully illuminated. But there is a region in between, right, where the blocker is partially blocking, partially occluding is the technical term in graphics, the light source. And then you get sort of a partial coverage. And if you look closely here, every pixel here is either black or white, okay, because we only cast one ray randomly in order to estimate that integral. But you start to get a visual sense of this soft shadow already. So this would be the difference between quadrature-based integration and Monte Carlo or random-based integration for this case. As an example, the true answer, right, looks something like this. Okay, it has grayscale values in here. And so these two are, very efficient computational estimates of this true answer. But this answer, in a certain sense, is capturing something that's closer towards the answer that we're aiming for. Of course, what's going to happen is that in the quadrature-based method, we would just take more and more samples. We'd super sample, right, the light source. And in the Monte Carlo sense, we would take more and more random samples over the light source, and both would eventually converge on the true answer. All right. So overview, Monte Carlo integration. The idea is to estimate the definite integral that we care about based on random sampling of the underlying function, okay, of the integrand of that function. The advantages are, this is a very general method. It's relatively simple to implement. We'll go through some of the random sampling requirements that take a little bit of a technical implementation, but it's relatively simple. It's very, one of the reasons it's very general is that it only requires us to evaluate the function at a specific point, which is something that we can often do. And for that reason, it works for very general functions, okay? In fact, it works for very general functions that may be very ill-behaved in a mathematical sense. This method of solving or estimating integrals works even if the underlying function has very sharp discontinuities and other kinds of bad mathematical behavior in very general sort of settings. It's efficient for high dimensional integrals, as I described intuitively, this cursive dimensionality. But there are disadvantages too. Okay, Monte Carlo integration is not like some magic silver bullet that will just solve all your integration problems in a beautiful and efficient way. The problem, as we already saw in this picture, is that you get noise. Okay, your integral estimate is going to be a random variable. That random variable is only going to be correct on average. Okay, so any particular estimation, random estimation you do is going to have some error, random error associated with it. And in order to drive that error down, the random error down, you want to take more samples. But that can be slow to converge. You might need to take a lot of samples in order to get a low noise estimate of the integrals that you care about. Okay, so that's the overview of Monte Carlo. In this lecture, we're going to get into all the details of how we do Monte Carlo integration through a bunch of different examples. Okay, let's get going. This is random sampling, okay, in order to estimate integrals. So we're going to do a lot of things related to randomization. And so I'm going to start with a probability review. Random variables. We're going to use random variables a lot. Okay, so I think we've all used a random variable function, okay, probably in the coding that we've done before, rand 0, 1 or some equivalent in APIs that you've used. Mathematically, what are we talking about here? I'm going to use notation for in this lecture where a capital X or a capital variable might denote a random variable. That means that this random variable represents a distribution of potential values. And if I write something like capital X, that random variable is tilde of P of X. That means the random variable X is drawn from a probability density function P of X. Then the probability density function in this case is P of X. And P of X describes the relative probability of a random process choosing this specific value, little x here. Okay. So for example, if P of X was like a bell curve at the origin, then it'd be more likely to choose 0 values and less likely to choose increasing values, like following like a Gaussian distribution, as one specific example. We'll look at other examples today. Here's another example. In this case, a uniform PDF probability density function, all values over the domain being equally likely, such as a die, okay, like a die that you could roll. In this case, the capital X here, the random variable X, takes on specific values, only 6 discrete values, right? Only 6 sides to the die, 1, 2, 3, 4, 5, 6. And the probability density function of these values is P of 1 equals P of 2 equals P of 3 and so on equals P of 6, because they're all equally likely. And the probability is going to be 1/6. Let's talk a bit more about that probability density function, and we'll build up from these simple examples to the continuous case. So for a probability density function where there are exactly little n discrete values or discrete possibilities for little x sub I, the values that the random variable could take on, then we can think of the probability that in this PDF, each of those discrete values is chosen. And in particular, the probability that we choose little x sub I will be denoted P sub I, okay, at least as I'll use it in this lecture. So here's a little cartoon. In this case, there's 4 specific values of x sub I, and P sub I here is this little bar chart shows P sub I is the probability you choose it. So we're much more likely to choose the second choice here, and then the fourth and the first are roughly the same, and the third one is much less likely, okay? What are the requirements of this probability distribution? There's only 2 that we'll rely on, and they're very intuitive, right, for probabilities. The P sub I is the probability that we choose any specific value, x sub I, has to be non-negative. Okay. Of course, we can't have a negative probability that we choose a choice. That's just by definition. And we want to make sure that to make sure it's a probability density function, the probability that we choose one of these choices, x sub I, is 100%. Okay, so that means that the sum from I equals n up to little n, where there's n discrete values, the sum of the P sub i's has to exactly equal 1. Okay, 100% probability that we choose one of these. This is like, really not rocket science. It's a very basic sort of assumptions. But I'll tell you, this simple one here, summing from P sub I up to 1, is a really important normalization criterion that we'll have to take take a lot of care to ensure that this is enforced in some of the calculations that we come back to later. So coming back to the 6-sided die example, P sub I is 1/6. We all know that if you roll a die, the probability of any face is going to be 1 out of 6. And the way to think about it in terms of this constraint here is that the sum of the P sub i's have to equal 1. And therefore, since they're all the same, because each side of the die is equally probable, then it's 1 divided by 6, okay, is the probability density function here. Okay, moving right along. Expected value of a random variable is going to be really important for us. So what is the expected value? It's just the average value that we would obtain if we repeatedly draw random samples from that probability density function, from that probability distribution. If capital X, again, is that random variable drawn from that distribution, and there are little n discrete values x sub I with probabilities P sub I, then the expected value of capital X, which we can write E for expected or expectation with square brackets of that random variable capital X is the notation that we'll use, is equal exactly to the sum of each of the possible values x of I that we could get randomly multiplied by the probability that we actually get that value, which is p sub I. Okay, so it's the sum from I equals 1 up to n of x of I times p sub I. Now, this is pretty intuitive, right? So, this one, for example, x of I, we're much more likely to draw this value because it's much more probable. So we just weight that value more in this sum. And the probability that we get this x of I over here is small, and it's going to contribute less to the overall weighted sum or expected value of this random variable. In the die example, okay, the expected value of capital of this random variable, that is the expected value of the number that we get on the die when we roll it, is equal to what? It's equal to sum of I equals 1 up to n of I, right? 1 up to 6 in this case, divided by p sub I, which is 1 over 6. And if you write that out, it's actually 3.5. Okay, so the expected value in rolling a die is 3.5. Okay, that was the discrete probability case. And then most of the things that we'll look at, though, for this course are going to be dealing with continuous probability density functions or probability distribution functions, synonyms, not the discrete case that I just looked at. So in this case, capital X, if drawn from P of X, where P of X is a continuous probability density function, is a random variable X can take on any continuous set of values, and it's the relative probability, P of X gives the relative probability of a particular value being chosen. The conditions on P of X are exactly the same as we said before for the discrete case, okay? But it becomes a little bit less trivial in this case to enforce it because we have to think of continuous integrals. So P of X has to be greater than or equal to 0, has to be non-negative, right? We can't have a negative probability of choosing a value. And the choosing at least one of these values has to be 100%. So the integral of P of X dx has to be equal to 1. The expected value of X is just the same as a summation, but we take the limit, as this, the number of values goes to infinity, and we take it, the summation or the discrete sum turns into an integral. So the expected value of capital X in this case is equal to the integral of X, the value, times P of X, the probability we choose that value, integrated dx. Okay, so all this by direct analogy to the discrete case. The next thing is that we will rely a lot on considering functions of a random variable. Okay, this is going to be really crucial to formulating complex integrals, complex in the sense of complex functions of a particular random variable inside the integrand of the discrete integrals that we want to compute. We'll see examples of that today. So a function y of a random variable x is also a random variable. Okay, so if capital X, the random variable, is drawn from PDF P of X, and if random variable y is equal to function f of capital X, then the main thing that we'll be interested in is the expected value of that function of the random variable, the expected value of y. And we can write down that the expected value of y is equal to the expected value, in this case of f of x. And what is that? That's going to be equal to f of x times p of x dx, actually just straight from the definition of the expected value of a random variable. We just substitute that f of x in here inside this integral, okay? Simple to see, very important, and we'll come back to rely on this in a number of ways in this lecture today, okay? So I'll just say it again, the expected value of a random variable y, where y is equal to f of x, so the expected value of f of x is equal to the integral of f of x times p of x dx. All right, easy definition to write down, and we'll look at some specific examples to gain a lot of insight and intuition about this as we go today. Okay, Monte Carlo integration. Monte Carlo integration. Again, this is just it's a very simple idea, very simple, very powerful. Estimate the integral of a function by averaging random samples of the function's value. Okay, pick random locations inside the domain of integration, evaluate the function, and use those function evaluations to estimate the integral. That's the idea. So in this cartoon, again, we have, as I showed in the first slide today, a definite integral of f of x dx from a to b. This is, again, the picture here, but before, where with quadrature, we would choose, structured regular samples, sample locations here, and we'd apply like, rectangle rule, trapezoidal rule. Here, it's different. We choose these random sample locations inside this interval from a to b. We evaluate the function at each of these random locations, and then we're going to try to estimate the area under the curve from these random function evaluations. Okay. Yeah, thanks. That's right. What's P of X again? P of X is, on the previous slide, P of X is the probability density function of the random variable capital X. P of X just says, hey, I'm going to choose, I have a random variable. Now I'm going to choose what the random value is. I'm going to draw a sample from that random distribution. What value did I get? P of X tells us how likely it is that we get any specific little x, okay, when we take that random sampling. I'll have some more cartoons of that later and some examples that might clarify and build that intuition as we go. Okay, so again, all right, integral f of x from a to b dx. Monte Carlo integration. We're now going to define the Monte Carlo estimator for the definite integral of that function f of x. Again, here's the definite integral that we're aiming to evaluate. We'll have a random variable. In this case, we're going to take a number of samples. Okay, so I'm just going to add a little subscript here, sub I, so that instead of just one capital X, which would be one random variable, we're going to have n versions of this. So we'll just label them x sub I. And they're going to be drawn from this probability density function P of X. The Monte Carlo estimator is this expression here. Let's just go over it. The Monte Carlo estimator, capital F sub n, which is an estimate of this definite integral here, where we're using capital N samples, random samples, is given by this expression. It's given by the average, as you can see, 1 over capital N times the summation from I equals 1 up to capital N of what? Of f of capital X sub I divided by P of capital X sub I. Okay, so what's going on here? We take n samples drawn from this probability density function. We take n samples, we get n little x values, right? We evaluate the function f at each of those random x values. And then what this is saying is we evaluate the function there, we divide it by the probability that we chose that specific little x, okay? And then we just average that. And what this slide is saying is that if we do all of that, we will end up with an estimator. We'll get a number, right? And that number is our random estimate for this definite integral here. What is P of capital X sub I? Good question. So again, it's okay. So for each of the x sub i's here that we're going to evaluate in a random sense, right? We're going to choose a sample from what? From this probability density function here. That gives us a specific value for x sub I. We evaluate the function f at that location, and we evaluate p, the probability density function, at that value. And we take this quotient here, this ratio, and then we average those. If x sub I is a contiguous random variable, then p of x sub I equals 0. Good question. It won't be. It's a probability density function, so it'll give the relative probability of choosing that. Hold that thought. We're going to look at some specific examples of probability density functions, p of x, later, okay? So I promise I'll come back to that, and it'll be clear why it's not 0 when we look at those examples. for all capital X sub i's, do we need the same P of X? Great question. We don't. This specific Monte Carlo estimator that I'm showing here assumes that all n samples are drawn from the same probability density function. You could come up with more sort of, sophisticated schemes where subsets of these random variables are drawn from different probability density functions, and you combine all of them in different ways. In fact, there are sophisticated versions of Monte Carlo integration that use those sort of techniques. Okay. So this is not done. I'm just introducing a definition here. Okay, we're going to look at and prove that this is this estimator has good properties. But this is a general and very useful Monte Carlo estimator that we'll spend quite a bit of time with. Let's look at a specific special case of this that we'll call the basic Monte Carlo estimator. The basic Monte Carlo estimator is a simple special case where we're going to sample that integration domain with a uniform random variable. Okay, a uniform random variable. And what does that mean? A uniform random variable is just a random variable that's drawn from a probability density function P of X that's a constant. Okay, P of X, of course, could be any function of X, but in this case, we're saying for a uniform random variable is that it's a constant, which means that it's independent of X. That means the probability we choose any particular X is equally likely. Okay, so what does this look like? So here, for example, is some f of X that we care about. The area under the curve here is the definite integral that we're trying to evaluate in the top. In the bottom, this is P of X. This is the probability density function over the interval of integration from A to B. If it's a uniform random variable, then the probability we choose any of these specific X values is the same. Okay, it's a constant as shown here by a horizontal line. Okay, it's constant. Now, right away here, you can see actually a first example of why P of X is not going to be zero in this probability density function sense, even though we can choose any continuous X here. Remember, the requirement for this P of X to be a probability density function, or one of the two requirements, is that it integrates to 1 over the domain of integration from A to B. So if the integral from A to B of P of X dx is equal to 1, and we have assumed P of X is equal to a constant C, then we can just plug this in and solve for it, right? The integral of A to B of a constant C dx equals 1 is going to imply that C is equal to 1 over B minus A. Okay, just the height of this thing here. So we 1 over B minus A, because then times, B minus A, the length of the interval, we're going to get an area under the curve of 1. Okay. So this might start to answer the question by, algebraically, very simple algebraically, for why P of X is not a 0 in this domain, even though it's a continuous choice of X. Okay. Now let's go to the next step. So the basic Monte Carlo estimator, again, it's just the special case where we use a uniform random variable. So this was the Monte Carlo estimator that I wrote down before. And we can just plug in P of X sub I is equal to what? We just derived it in the previous slide. It's 1 over B minus A, where A and B are the beginning or the endpoints of the integration domain. And we can just rearrange terms here a little bit and clean this up. We're going to get the basic Monte Carlo estimator F sub n is equal to B minus A over capital N times I equals 1 up to n of F of X sub I. So what happened here? We're saying that, okay, to estimate this integral, just draw uniform random samples inside that interval, evaluate the function, average all of those values, right? That's just 1 over n times all of these samples that we drew. And then the average of all the samples multiplied by B minus A, which is the length of the integration domain. Okay, so just to sum up some of the things that I wrote down here. Okay, again, for the basic Monte Carlo estimator, definite integrals here, uniform random variable, P of X is equal to 1 over B minus A. We derived that. And then the basic Monte Carlo estimator is shown here. Again, capital F sub n equals B minus A over capital N times the sum of all the random function evaluations F of X sub I. Okay. Okay, so far I've just written down very concretely some Monte Carlo estimators. I said, okay, here's some magic equation here that I say we could use. We could, evaluate this, and then we could use it as a numerical estimate for this definite integral. Okay, well, is this a good estimator? Okay, that's what I want to talk about next. And I want to try to show you that this estimator has some properties that are quite desirable. The first one property is that these estimators are unbiased. They're unbiased. Definition: a randomized integral estimator is unbiased if its expected value is the desired integral. Okay, there's a few things going on here, so let's just unpack that. Okay, so we wrote down capital F sub n, that is a randomized estimator for the definite integral. Okay, so that's capital F sub n is an example of a randomized integral estimator. And we say it's unbiased if its expected value, what's going on there? The randomized integral estimator is a random process. Remember, because we're choosing random sample locations in order to evaluate the function. We can do that again and again, right? If we drew 10 samples, estimated the integral, we get a number. If we do it again, we'll choose 10 different random locations and we'll get a different random number for estimate for the integral, okay? So capital F sub n is a random process. We'll get different values every time we run it randomly. What's the expected value of it? That's something we'll have to calculate. And what this is saying is that we want the expected value of that randomized integral estimator to be the desired integral. Here's a fact, okay? Claim. The claim is that the general and basic Monte Carlo estimators that I just wrote down are unbiased. I'm going to prove that on the next slide. Now, and I think it's seems pretty intuitive that we want unbiased estimators. Like we want the expected value to be to be the desired integral. That seems like a reasonable, plausible thing to do. And maybe we could take it up in discussing it online. Are there any estimators that are unbiased? Why would anyone do that? The answer is that if you can get an unbiased estimator that has a lot of things that are really useful, you can depend on, so you'd like that. There are some engineering trade-offs in some cases where you may tolerate an unbiased estimator if you understand the ways in which it can be unbiased, because it might give you some more engineering efficiency. Okay, we'll leave that. We're not going to go deeper into that into this lecture. But we're going to focus on unbiased estimators today. Yeah, great question. How do we know that this has an expected value that's close to the integral? Doesn't that imply that we know the integral already? Great questions. We're going to prove right now that the expected value is not just close, it is equal to the definite integral, but it does not imply that we know the definite integral already. Okay, we'll look at both of those really good questions as we go here. First, let's go through the proof that the Monte Carlo estimator, and we'll just do the general case because the basic one was just a special case of this one. We'll prove that the general Monte Carlo estimator is unbiased. Okay, so we got expected value of capital F sub n, and we just substitute in the definition of this. So that where we're going in this proof is that we're going to want to derive this, and at the end, we're hopefully we'll see that this is equal to what? Equal to the definite integrals. We hope it's going to be equal to the integral from a to b of f of x dx. Okay, that's where we're headed. All right, so how do we tackle this? We need two properties of expected values. I'm not going to derive them here. These are well-known, not trivial, but well-known basic properties of expectations in probability. I'm just going to state them here. If you haven't seen this before, that's okay. You can just sort of take them as statements of fact here. But I strongly encourage you, if you haven't seen this before, to go look this up, or we can discuss it online where these come from. Okay. The two properties of expected values that we're going to rely on are, number one, the expected value of of a summation of some random variables y sub I is equal to the sum of the expected values of each of the random variables. Okay. And so in other words, the expectation can push inside a summation is a way to think about it. The second property that we're going to rely on is that the expected value of some random variable y multiplied by a scalar value, so a here is some scalar, is equal to a times the expected value of y. So a scalar value can move outside or into an expected value. We're going to apply these in this proof. It's going to go pretty swiftly. Okay, so let's take a look. Let's go back over here. We have expected value of this definition of the general Monte Carlo by estimator. we can use these two properties to do two things. We can use the second property to pull the 1/n outside, and we can use the first property to push the expectation inside the summation. So now we have the expected value of this Monte Carlo estimator is equal to 1/n times the summation from I equals 1 up to n of the expected value of f of x sub I divided by p of x sub I. In the next step, we're going to apply the definition that I described earlier for the expected value of the function of a function of a random variable. And a couple of things are going to happen here. Okay, so just recognize this thing inside this expectation is a function. Okay, this is the function is f of it's a function of capital X sub I. The function is f of x sub I divided by p of x sub I. Okay, but if you think that sort of two functions is too complicated, recognize you could just rewrite this inside here as a g of x sub I. So I'm not going to write this down in this slide, but you could write it down as expected value of g of x sub I, where g of x sub I is just equal to f of x sub I divided by p of x sub I. Okay, we're not going to do that. It's just sort of a little algebraic notation to make really clear what's going to happen on the next slide, which is applying that definition from a few slides back of the expected value of a function of a random variable. And what happens is that it's going to be that function of the random variable times the probability of selecting that x integral dx. So this expected value here is actually equal to the definite integral from a to b dx of f of x over p of x times p of x. Okay. Now this might look almost too good to be true. Let's just crank it out and then we'll make a couple of comments about this. Okay, the p of x is obviously now cancel exactly. So we get the integral from a to b of f of x dx and then summed n times and then divided by n, which of course this summation is just going to give us capital N times this definite integral divided by n. So the whole thing is going to cancel out. And we're just going to get our goal, which is equal to integral a to b dx of f of x. No kidding. All right, closed form proof. Now, the key to hold this, aside from these basic applications of the definitions, which was just of basic properties, which is these two properties of expected values, and then this expected value of a function of a random variable, that's all just application of basic properties. The key thing that happened here, of course, was that we ended up with this expression here where the p of x is exactly canceled, giving us the definite integral that we cared about, and the p of x's completely fell out. Okay, this is no accident. Okay, that's why in the original definition of this Monte Carlo estimator, we divide by p of x sub I. In fact, you can see now that in this derivation here is that if we don't divide by p of x sub I in this Monte Carlo estimator, we're not going to get f of x integrated from a to b dx at the bottom. Okay, it's not going to happen. We're going to get the p of x carrying through as a factor in here, and we're not going to end up with an unbiased Monte Carlo estimator. That is why the unbiased Monte Carlo estimator has this division by p of x sub I from a mathematical proof perspective. But just to sum this up, the expected value of the Monte Carlo estimator is the desired integral. Woohoo, really good, really important, something that we definitely want to be able to rely on. The next comment I want to make is about the variance. Okay, that's the standard deviation, the error of this random variable estimate. Now, I recall from statistics or probability, definition of variance. So the variance of a random variable y is equal to this thing here, right? The expected value of y minus the expected value of y all squared, which you might recall from variance or statistics. If you've seen this before, you can sort of simplify it and prove that it's equal to this next thing here. The key thing that I want to have on this slide, just to remind us all of, is that the variance and therefore the standard deviation or the error in this random estimate is going to go down as we take a larger number of samples. How does this work? It's that, look, if we have a random variable y and we have a certain variance for it, we can ask ourselves, what is the variance if we take n copies of that random variable, we draw n samples from that same probability density function and average them. And if you apply these properties of variance over here, which again, I'm going to state These are similar to the properties of the expectation of random variables I had on the previous slide. These are just the equivalents for variance. Then you can plug these properties, basic properties of variance, into this and calculate out that the variance of an average of n versions of that random variable is going to be 1 over n times the variance of the single random variable. What does that mean? It just means that, right, if we take a single random sample, we'll get a certain amount of noise, right? We'll have a certain amount of variation to it away from the correct or the mean value, the expected value. If we take more samples and just average them, we just do it multiple times and average them, we'll get a closer to the mean value. The average will be closer to the expected value. And this is the rate at which the standard deviation will go down. The variance will go down by 1 over square root of n. And we can see that pictorially in this, I'll go back to this example of the shadow ray calculation. So again, all this was that, hey, we pick a point, a pixel in this scene on the ground plane to calculate the gray level in that for that pixel. We're going to cast rays towards the light source and see if they're blocked by this polygon over here or not. If they're all unblocked, we get a full intensity value. If it's all blocked, like underneath this blocker completely, it's going to be completely black. If it's in this penumbra region, then some of those rays will get blocked. Some of them will hit the light source and we'll get some intermediate value. If we do it with one shadow ray, we'll call this a shadow ray tracing, okay? We'll see that we get this kind of an image, which is very noisy in this penumbra region. If we take 16 shadow ray calculations, that would be like just doing the same random process on the left-hand side, but doing it 16 times and averaging the images, then we get a cleaner looking version of the image, okay? So that's just an expression of that, a visual version of that variance, of the result of that variance slide that I showed before. Question here, are the y sub i's independent? Yes. So you can think of these as IID in this case. So all these y sub i's, I didn't write it explicitly on this slide, so thanks for that question. Think of all of these y sub i's similar to the definition in the Monte Carlo estimator. All of these y sub i's drawn from the same probability density function. Okay, good. All right, so what are the big ideas here? Okay, we made a lot of progress. We have a specific equation that is procedurally clear how we can evaluate it through random sampling of the function that we're trying to integrate. And we get a random estimator of the definite integral that we care about. And we have this notion that if we just take more random samples, okay, we'll get an estimate of the integral that is closer to the true answer. It's going to have a standard deviation from that true answer that is going to go down as we take more samples. Okay, so this is great, right? Now we have Monte Carlo. We have a very general procedure, okay? You just, you have some function, you're trying to make a numerical integral of it over a specific domain. You could just sample that function and then perform that Monte Carlo estimator I showed you. And if you have the time, you can just draw more and more and more samples, and you will get closer and closer and closer to the true definite integral. That's pretty nice. Very general, very, very useful. Okay, and it's up to you how much time you want to spend, how much time you have to spend on estimating. All right, let me keep going. So far, we've looked at just 1D versions, right? Integrals of f of x dx from a to b. But I just want to point out, it's a very general domain of integration that can be a Monte Carlo integration can be applied to. So let's just look at it explicitly. For our first example, let's look in 3D, okay? So let's say we will have a function in 3D, f of x, y, z, and we want to integrate it volumetrically, dx, dy, dz, over some box in space from x0 to x1, and y0 to y1, and z0 to z1. If we would take a uniform 3D random variable, and I did it for 3D here, but you'll see that this generalizes to arbitrary n-dimensional PDFs. Capital X sub I in the 3D sense is going to be given by a probability density function P of XYZ. And by exactly the same logic as I showed for the 1D case, we're going to find that this PDF, P of XYZ, is going to have to be equal to this expression over here, right? It has to be 1 over the volume of this domain of integration. And the volume of the domain of integration is x1 minus x0 times y1 minus y0 times z1 minus z0, because those are just the lengths of the rectangle in 3D space, lengths of the cuboid in 3D volumetric space. Therefore, the basic Monte Carlo estimator in 3D, capital F sub n, is going to be equal to this volume of this domain of integration times the average 1 over capital N times I equals 1 up to N of little f of capital X sub I. Now notice here, capital X sub I here is now a random variable that's actually a 3D coordinate, right? You can see here, capital X sub I is drawn from P of XYZ, so you get, like a random location in XYZ. So mechanistically, what does this mean? I have a 3D function. I have a volume, a box in volumetric space I want to integrate. I'm going to choose random locations inside that 3D box. I'm going to evaluate the function volumetrically at that location, average all of those values, and then I multiply by the volume of that box. This is the 3D version of the basic Monte Carlo estimator, okay? But it goes on from here. We can use Monte Carlo estimation for all kinds of things, and then the complexity in applying it correctly is going to go back to like stuff that you remember from integral calculus. Okay, it's going to go more to like, okay, can you set up the derive the integral that you want to evaluate, and the integrand inside, the function inside the integral correctly? Can you specify the domain of integration correctly, including any algebraic factors that appear if you want to do a change of variables, change of basis, for example, for integration, all of that kind of stuff. Let's take a look at a few examples, okay? And this is what we'll get into sort of implications with respect to noise and efficiency. Let's take a look at the direct lighting integral again that I showed earlier. Again, the irradiance at a position P equal to this integral that I showed earlier, where L, again, here is the radiance arriving at position P along a particular direction, omega. The idea here for applying Monte Carlo will be that, and I apologize, I left out the domain of integration here. It's going to be H2. Again, H2 is the hemisphere that sits over this point of integration. We're going to sample directions over this hemisphere, okay, randomly in solid angle, where the solid angle is, again, half of the sphere enclosing sphere. The estimator is going to be given, this example is going to be, the idea will be to draw them uniformly, randomly over the hemisphere. So how do we do that? And what's the math involved? If capital X sub I is drawn from a probability density function P of omega, where omega is a random direction on the hemisphere, then what is the probability P of omega? We know it's a constant. What is it exactly? It's going to turn out to be 1 over 2 pi. 1 over 2 pi. Why 1 over 2 pi? Because omega is drawn over solid angle space. When we looked at you folks looked at solid angles in radiometry, the solid angle of a full sphere, right, is given by the area of that sphere divided by the radius squared of that sphere. So it's 4 pi r squared, formula for the surface area of a sphere divided by r squared. So the solid angle of a full sphere is 4 pi. Therefore, the solid angle for a hemisphere is 2 pi. And in order for P of omega to be integrate to 1 over that hemisphere domain of integration, P of omega is going to have to be 1 over 2 pi, okay, so that it integrates to 1 over the hemisphere. It's similar to what we looked at for the uniform sampling in the 1D case. Then we have y sub I, the thing we're going to integrate, equal to f of x sub I, and we can define y sub I to be this expression inside the domain here, okay? It's L times P comma omega sub I, and where omega sub I is the random direction, times cosine theta I. Cosine theta I is just this Lambert's law correction term here. Okay, so now we have the Monte Carlo estimator, capital F sub n is equal to 2 pi over, this is exactly from the formula that we looked at earlier for the basic Monte Carlo estimator. It's equal to 2 pi over capital of N times the 2 pi rather times the average value of y sub I with n random samplings of y sub I. N random samplings over the hemisphere. That's the math that draws that lighting integral case exactly to the math that we looked at earlier. Let's just talk about it in terms of like some pseudocode. Okay, so we're going to sample directions over the hemisphere uniformly in solid angle. And so if I give you a surface point position P, we'll initialize the Monte Carlo estimator that we care about, capital F sub n, to 0. And we're going to accumulate in it as we do n repeats of drawing a sample. So for each of n samples, generate a random direction, omega I, that's just a random direction on the hemisphere, compute the incoming radiance to the point P from that direction, omega sub I, How do we do that? How do we get the incoming radiance? Okay, so that's next lecture. We started to talk about it already with ray tracing before, but a ray tracer and a global illumination ray tracer in particular is the machinery we're going to build next time that will give us a function call programmatically to evaluate the radiance along this ray direction. So compute the incoming radiance, arriving at position P in that direction, omega sub I, and then we increment the Monte Carlo estimator, f sub n, by incrementing it by that integrand, 2 pi over capital N times L sub I cosine theta sub I. And then when we're done, capital F sub n will be our estimate for this irradiance integral. Okay. All right. So that's a demonstration of applying exactly the same principles we talked about, but this time in sort of like polar coordinates and applying the kind of radiometry or lighting measurement concepts that we had from previous lecture. But there's a problem. Okay. So what I just described will totally work. But if you apply it exactly as I described to that picture I showed before, very simple picture, right, which was a light source, a small area light source with a blocker over like some ground, and you actually did not one sample, but you did 100 samples, okay, 100 different ray directions on the hemisphere, you get the picture that looks like this. You still see like a shadow here, you still see sort of a fuzzy boundary, but you know, this looks really noisy, okay? Really, really noisy. So what happened here? Let's just reason this through, okay? What's happening here is we're sampling 100 rays, but the 100 ray directions for every point on this ground plane, 100 rays, they're drawn randomly over the full hemisphere that sits on top of that ground plane position. So why does the image look noisy? Look, I just drew 3 of the pixels here. You're going to actually, through the ray directions, it's actually going to be 100. Okay, random directions, but you can see geometrically what's happening. You choose all these ray directions. What is the probability, okay, for this surface position on the ground plane that you're going to choose a ray that hits this light source over here? The light source is pretty small from the perspective of this point on the ground plane. It has a small solid angle, right? So the probability you hit it is really low. And most of the time you just cast it in these totally random directions where it's, you know, there's no light coming from there. So you just get a lot of 0 values in this estimate. That's the reason that this image ends up looking noise. And in particular, if you go to the neighboring point over here, pretty close to this one, you're going to choose 100 random directions that are different random directions than the one here. And, you know, this one may be unlucky and all 100 random directions may completely miss the light source. That's the reason why, you know, many of these particular outlying positions over here are mostly black and some are randomly are bright, okay? Good question. Someone asked, Devin asked, could you just choose a random ray from this set that hits the surface of the light? Yes, great idea. That's the right intuition, and that's exactly where we're gonna go, okay? That's the kind of intuition geometrically that is really clear to us in looking at this picture. And we're going to talk through how we can apply that in Monte Carlo integration. Okay, it's going to be called importance sampling. Easy to say the idea exactly, and then implementing it is also relatively straightforward to go through, but it involves quite a few technical steps, and we're going to walk our way through that. So this Monte Carlo estimator that I just described uses different random directions at each pixel. And the observation, just as Gavin described it, is that the incoming radiance is 0 for most directions in this scene. And a simple idea that seems like it'll work great is that wouldn't it be great if we just integrate over the directions that actually have a chance of hitting the area of the light source? Only choose directions where the incoming radiance could be non-zero, okay? That looks more like this picture, okay? So for each of these 2 positions shown here, we cast rays, say 100 rays, but the 100 rays all will be in directions that are subtended by this area light source over here. If there's no occlusion present at all, like for this yellow position, then all 100 rays hit it and we get a full brightness light source. If you're at this green location here, then some of the rays will strike the light source, but not all of them, and you'll get some partial, you know, lighting coverage over here. Okay, so this is the simple sort of intuition. And you can apply names to these 2 types of sampling schemes. You can think of these as 2 probability density functions, random sampling functions of directions over the hemisphere of directions at each point. This one over here, on the left, we can call it sampling solid angle. Solid angle just means all directions uniformly is the name we can give it. So 100 random directions on the hemisphere. On the right-hand side, we're sampling just the light source area. So this is 100 random points on the area of the light source. And here, the key idea, of course, is that it's only important to sample directions that could hit the light in evaluating this integral of the lighting contribution to positions on the ground plane. Another question, Gavin asked, would you have to iterate over all light sources to compute this, or maybe randomly select light sources? This is exactly the right intuition. This scene only has one light source. If you have multiple light sources, you can't only sample over one light source. You're going to have a problem, right? You're going to not see the shadows or light contributions from others. So you're going to have a way to sample over all those other light sources. And there's different ways to do that randomization. In the programming assignment that you'll have related to this part of lecture, we're going to get you to do exactly that. There will be multiple light sources, and you're going to implement random sampling over a group of light sources. But to connect this idea here, we make the simple observation that the only important directions to sample in this case, for this particular example, are the directions that could hit the light source, because those are the only directions where light could actually transfer to the ground plane, where the integral here could be non-zero. The integrand could be non-zero. We're going to generalize that now and think of that as, where is it important to sample this probability density function? The topic here, very, very general topic in Monte Carlo integration, is importance sampling, okay? Importance sampling, another really simple, fantastic idea. The simple idea is, in Monte Carlo integration, we want to sample the integrand according to how much we expect it to contribute to the integral that we care about. We want to sample the integrand according to how much we expect it to contribute to the integral. More specifically, we want to sample the integrand where the integrand is big, okay, where the function has large values, because that is where it's going to contribute to the integral. Okay, let's look at a cartoon. Let's say we have an f of x here. Okay, it's kind of like this bumpy complex function, integral a to b f of x dx. And the basic Monte Carlo estimator, as we talked about, would just sample this uniformly. But if we sample uniformly, we're equally likely to pick positions out here at these large x values where the f of x value is very small, and it will contribute very little, numerically to this overall direct integral. Okay, and that's going to be inefficient. Okay, to sample in these areas, small contribution to integral. Instead, importance sampling would say, well, first of all, you have to have some kind of intuition about your integrand, okay? If someone gives you some black box piece of software with an f of x and you don't have any information about f of x, then you're going to be a bit hard pressed to apply this next insight. But if you have a little bit of intuition about where the integrand might be large, not perfectly all the little ripples and details, but roughly there's two humps, then you might say, I want to sample from a probability density function that has this kind of shape to it. And therefore, I would be much more likely to sample from underneath this big hump here and this hump over here. And this would give me a better estimate, a more efficient estimate of this f of x dx integral. So importance sample Monte Carlo is actually just the general Monte Carlo estimator that I described before, but now we have a better sense on what p of x probability density functions we should aim to use. It's just this same Monte Carlo estimator from before, but now the p of x is, we're going to try to shape the p of x according to our intuition or our background knowledge as best we can in order to sample from where we think the integrand is going to be big. Okay, the intuition here is, look, if I sample, why do we have this ratio? Why do we want to sample more from big areas? The intuition is, if I sample x less frequently somewhere, then each sample that I draw there should count for more. Okay, so for example, with this p of x here, I'm less likely to sample, there's still a small chance, but it's small, that I'll sample from these big x values over here. If I do happen to draw a sample from there, then it should count more. And that happens numerically because I'm going to divide by p of x. So if I happen to randomly pick an x that's large in this area over here, evaluate f of x, and then I'm going to divide it by p of x, which is small. Dividing by p of x is going to weight that sample higher. Okay, so again, intuition, if I sample x less frequently, each sample should count for more. And then as a technical note, I had this on a previous slide too, but I didn't emphasize it there. Let me just note it again. Look, one key thing here intuitively is that the P of X you choose here, there's some rules, right? It can't be a zero anywhere that the actual F of X is non-zero. If it was actually zero somewhere and F of X was non-zero there, then we would never be able to, sum the contribution of that part of the integrand, and we would get we'll get a biased estimate of the overall definite integral. I'm going to leave this slide for us to talk about in discussion on the web, and just come back to this. So this thing I described earlier, this is just importance sampling, applying our knowledge, right, that the light source is located in this part of the 3D space. So how do you sometimes have information about the integrand that you're trying to integrate? Here's an example, okay, geometrically that emerges, and then using that knowledge to sample, to do that Monte Carlo integration is something that you can aim to do and get a much cleaner result much more efficiently with the same 100 samples. Now I want to show you, though, technically what has to happen in order to actually perform this integration between these two things. And if you're thinking ahead about this and seeing where this might go, it's going to turn out to be a change of basis of the integration, okay? So changing the basis of integration from spherical coordinates, essentially sampling the hemisphere, in this case, like this, to integrating over the surface of the light sources. Okay, so it's the same value, right? This integral that we are aiming to get here for a certain position on the ground plane is going to give us a number, right? It's going to give us a real number, and we want to get the same real number as if we do by sampling over the surface area, over the area of the light sources. In this case, this is a picture for a general light source here, some kidney-shaped object out in space that's emitting light. And A prime is some differential area on the surface area of that light source. This is classic change of basis of integration, okay? And I just want to walk you through it. There's some important details. The specific algebra on it, which relies on radiometric calculations and geometric deductions, are not the focus of what I want to spend on these two slides. The big idea I want to get across is that it's a change of basis. And just like any integral change of basis, you got to dot all the I's and cross all the T's in the variable relationships. And there's going to be certain algebraic function factors that pop out in that change of basis. It's all very natural. And let's see what happens here. Okay. So this irradiance calculation, E of P, that's this over a solid angle, d omega here. If we go over integrating over the surface area of the light sources, it's going to end up with a few other terms that emerged here. Okay, why did that happen? Let me just walk you through it and comment on them without deriving them in detail. We're going to change the basis to dA prime. dA prime, again, is a differential area over the surface area of this light source. When we change to dA prime, the key is that d omega, which is a differential solid angle centered on a direction omega, there's a change of basis a term that's going to end up looking like this. It's going to be dA prime, which is the differential area over the surface of that light source, times cosine theta prime. Theta prime is what? It's this angle here, okay? And this term exists because geometrically, if the dA prime, the differential area, is tilted really far away from the direction that we care about, the projected area is going to be less, okay? So this is a geometric change of basis correction factor. And the differential area in terms of solid angle is going to be less if it's much further away from the definition of solid angle, right? So dA prime needs to be divided by the square of the distance between P prime and P. That's why there's this term over here as well. Changing from d omega to dA prime, therefore, ends up with this term here, cosine theta prime, and P minus P prime over all squared. Cosine theta just comes from the cosine theta in the original definition. Okay, that's the Lambert's law term. There's a couple other terms here that exist as well. The incoming radiance before at the position P is now going to be converted to the outgoing radiance. That's the light emitted from this light source at the position P prime, where P prime is the intersection of the ray exiting the position P in the direction omega, trace that into the world and hitting that light source in a particular position P prime, okay? So it's P prime here, and then omega prime, which is this direction that, this vector that goes in the direction from this differential area in the direction of the P that we care about. If that didn't all make sense, don't worry. That's what's going on here in terms of the radiometry. And to accomplish this change of variable in an algebraic correct manner, okay? One last term is that we have to have a visibility term, V of P prime, because the light source is here, but there may be objects in between these two positions, P and P prime, that might block the transfer of light emitted from the light source to arrival at P. So P prime here is just an indicator function, 0 if it's blocked, 1 if it's unblocked, okay? All right. And so mechanistically, what happens here, this is the formula now algebraically that we can derive for doing integration over the area of the light sources. And now what we do is we randomly sample positions over the surface of the light source. In the general case where it's a curved object like this case, it may be non-trivial to actually sample over the area of the light source. If it's just a rectangle in space, the example I showed before, that's pretty easy to do, right? A 2D sampling over that surface of that light source. Anyway, we sample, in this case, a uniformly over area, and then the Monte Carlo estimator for that integral, it turns out to be this thing over here. It's the integrand evaluated at that specific randomly sample point P prime, and then just applying the formula for the Monte Carlo estimator. Okay, so a bit of algebra here, quite a few additional terms, and the goal is that this function Monte Carlo estimator here with this y sub I is going to give us exactly the same output numerical value as the Monte Carlo estimator I derived some slides back over hemisphere, okay? But we know that if we apply this from the pictures that I showed you, that this Monte Carlo estimator is going to be a lot less noisy, okay? All right, so that's so that's how we tie through to our sort of algebra 101 change of basis, okay? And again, this is what the picture kind of looks like. Okay, those are some of the really big ideas that I wanted to convey to you in Monte Carlo estimation. Wait, what does this Monte Carlo estimator represent? Okay, good, yeah. On the previous slide, what does this represent again? This is the irradiance at a specific point P. In this picture, it's the irradiance at a point P on the ground plane or any point in the scene, which is the amount of light transferred, the amount of radiance deposited on that surface with the cosine theta Lambert term. Okay, so from the definitions of radiometry in the previous lecture. The other last but important detail that I need to cover is how to draw samples from a desired probability distribution. Okay, I haven't talked about that actually yet in detail, except for the uniform case. And so I'm going to start to talk about that now, and then we'll finish up this part of it next lecture and then get into global elimination. Okay, so let me begin it now. So the task, okay, is that I want to draw a random value from a given PDF, right? I have some function P of X that, I have a sense on what my integrand looks like, a function that approximates it. I want to draw a random sample. I want to write a piece of code that does that, that actually is proportional to the density of that function, okay? So given a PDF for a discrete random variable as a first example, where the probability for each x sub I is P sub I, the task is draw a random value for capital X, that random value, from this PDF. How we can do this is step one, we can calculate a cumulative, this is called the inversion method, okay, for performing this task, the inversion algorithm. First, we can calculate a cumulative PDF. We'll call it capital P sub j, which is equal to the sum from I equals 1 up to j of all the P sub i's. It gives us, in a cartoon form, a cumulative function in the discrete case that looks like this, right? So it's just the first P sub I here, then it's P sub 1 plus P sub 2, then P sub 1 plus P sub 2 plus P sub 3, and so on, okay? And when we get to the top, it's a total of 100% likelihood, okay? So that's step one. Step two then is, okay, give me a uniform random variable, psi here from 0 to 1, or eta. Oh my goodness, my brain's not working today. Whatever it is, Greek random variable, Greek letters. Anyway, from 0 to 1. Okay, so this would rely on some kind of system function to give you this random, continuous random real value between 0 and 1. Then we choose the capital X equal to little x of I, such that P of I minus 1 is less than this continuous value, which is less than or equal to capital P sub I. And there's a little bit of algebra. Pictorially, it's easy to understand. You can draw that random value from 0 to 1 in the vertical axis here, and you trace this across and choose the corresponding cell here. Okay. So how to compute this? You're gonna just make this table of these cumulative probability density functions, and then if I give you a particular random variable between 0 and 1, you can do binary search, okay, in order to find this closest cell. Thanks. I will go over this because we're at time next time, okay, in detail, but just pictorially, I'll go over these slides again in detail mathematically next time. I just want to say that discrete case that I just covered will just transfer geometrically exactly to the continuous case. The PDF in that case will be a continuous. If the uniform cases looks like this, but if the PDF is some general function, you can still calculate capital P of X, which is the cumulative density function, and you can apply the same inversion procedure, not on that blocky discrete staircase we looked at before, but some continuous cumulative density function exactly in the same way as before. It'll just turn into an inverse function of this cumulative probability density function. Okay, so I'm going to do that for you next time and show you an example of a specific function, say proportional to of f of x squared as the probability density function that we want to draw from. Okay. Hey, folks, so great to see all of you. And I will see you again next week. Have a great weekend.